In Part 7 of Lecture 2, we will discuss different architectural approaches to operating system design. The rate of change in the demands on operating systems requires not just modifications and enhancements to existing architectures, but new ways of organizing the operating system. A wide range of different approaches and design elements have been tried in both experimental and commercial operating systems, but much of the work fits into the following categories: microkernel architecture, multi-threading, symmetric multiprocessing, distributed operating systems, and object-oriented design. Most operating systems, until recently, featured a large monolithic kernel. Most of what is thought of as operating system functionality is provided in these large kernels, including scheduling, file system, networking, device drivers, memory management, and more. Typically, a monolithic kernel is implemented as a single process, with all elements sharing the same address space. A microkernel architecture assigns only a few essential functions to the kernel, including address spaces, inter-process communication, and basic scheduling. Other operating system services are provided by processes, sometimes called servers, that run in user mode and are treated like any other application by the microkernel. This approach decouples kernel and server development. Servers may be customized to specific application or environment requirements. The microkernel approach simplifies implementation, provides flexibility, and is well suited to a distributed environment. In essence, a microkernel interacts with local and remote server processes in the same way, facilitating construction of distributed systems. Multi-threading is a technique in which a process executing an application is divided into threads that can run concurrently. We make the following distinction. Thread, a dispatchable unit of work. It includes a processor context, which includes the program counter and stack pointer, and its own data area for a stack to enable subroutine branching. A thread executes sequentially and is interruptible so that the processor can turn to another thread. Process, a collection of one or more threads and associated system resources, such as memory containing both code and data, open files, and devices. This corresponds closely to the concept of a program in execution. By breaking a single application into multiple threads, the programmer has great control over the modularity of the application and the timing of application-related events. Multi-threading is useful for applications that perform a number of essentially independent tasks that do not need to be serialized. An example is a database server that listens for and processes numerous client requests, with multiple threads running within the same process. Switching back and forth among threads involves less processor overhead than a major process switch between different processes. Threads are also useful for structuring processes that are part of the operating system kernel as described in subsequent lectures. Symmetric multiprocessing, or SMP, is a term that refers to a computer hardware architecture described in Lecture 1, and also to the operating system behavior that exploits that architecture. The operating system of a symmetric multiprocessing computer schedules processes or threads across all of the processor. Multi-threading and SMP are often discussed together, but the two are independent facilities. Even on a uniprocessor system, multithreading is useful for structuring applications and kernel processes. An SMP system is useful even for non-threaded processes, because several processes can run in parallel. However, the two facilities complement each other and can be used effectively together. An attractive feature of an SMP system is that the existence of multiple processors is transparent to the user. The operating system takes care of scheduling of threads or processes on individual processors and of synchronization among processors. SMP has a number of potential advantages over uniprocessor architecture, including the following. Performance. If the work to be done by a computer can be organized so that some portions of the work can be done in parallel, then a system with multiple processors will yield greater performance than one with a single processor of the same type. This is illustrated in the following slide. With multiprogramming, only one process can execute at a time. Meanwhile, all other processes are waiting for the processor. With multiprocessing, more than one process can be running simultaneously, each on a different processor. Availability. In a symmetric multiprocessor, because all processors can perform the same functions, the failure of a single processor does not halt the system. Instead, the system can continue to function at reduced performance. Incremental growth. A user can enhance the performance of a system by adding an additional processor. Scaling. Vendors can offer a range of products with different price and performance characteristics based on the number of processors configured in the system. It is important to note that these are potential rather than guaranteed benefits. The operating system must provide tools and functions to exploit the parallelism in an SMP system. If the work to be done by a computer can be organized so that some portions of the work can be done in parallel, then a system with multiple processors will yield greater performance than one with a single processor of the same type. This is illustrated in the slide. With multiprogramming, only one process can execute at a time. Meanwhile, all other processes are waiting for the processor. With multiprogramming, more than one process can be running simultaneously, each on a different processor. A different problem is to provide the appearance of a single system for a cluster of separate computers, that is, a multi-computer system. In this case, we are dealing with a collection of entities or computers, each with its own main memory, secondary memory, and other I/O modules. A distributed operating system provides the illusion of a single main memory space and a single secondary memory space, plus other unified access facilities, such as a distributed file system. Although clusters are becoming increasingly popular and there are many cluster products on the market, the state-of-the-art for distributed operating systems lags that of uniprocessor and SMP operating systems. Another innovation in operating system design is the use of object-oriented technologies. Object-oriented design lends discipline to the process of adding modular extensions to a small kernel. At the operating system level, an object-based structure enables programmers to customize an operating system without disrupting system integrity. Object orientation also eases the development of distributed tools and full-blown distributed operating systems.